We modeled the weather to either be cloudy, rainy, or sunny. We know there are probabilities associated to each event, and if we observe the weather, so for instance cloudy, rainy, sunny, and so on, then we can infer these parameters from the data by the maximum likelihood estimate. But is there also a robuster estimate, or can we encode prior knowledge? And indeed we can. In this video we will derive the posterior and the map estimate for the categorical. Hi! Welcome to this new video. The agenda is that we will first look at the model describing the posterior, then we will make some general derivations, then we will first derive the posterior, then the maximum A posteriori estimate or map estimate, and later we will look at an example in TensorFlow probability in order to understand how the map estimate can help us with corrupt or noisy data. And this is also the motivation for this, and I already asked this in the introduction if there is a robuster estimate or if we can encode prior knowledge, because both of this is not possible with the maximum likelihood estimate. It works really well if we have a perfect data set, but once it is noisy or corrupt, it can lead us into a wrong direction. And here a map estimate, or in general a posterior, can help us to be more certain about our parameter inference. But before we start, let us quickly recall we have a weather variable w, and the weather is distributed according to a categorical. I mean, it's three states discrete, and this categorical takes a parameter theta, and the weather is within the set cloudy, rainy, sunny, and commonly we encoded this as 0, 1, or 2, or also in the one-hot categorical case, we encoded this with 1, 0, 0 as the vector, and 0, 1, 0 as the vector, and 0, 0, 1 as the vector. With this in mind, now let us start with the posterior derivation or with the map derivation. And for this, let us first look at the directed graphical model of what we will be judging about. And we have a data set with n observations. So let's say we have a data set with capital N weather observations, and these observations are of course associated with observable nodes. So let's call this a WI for the observation at the ith day, and we have them n times, so I will put them in a plate. And then we have a parameter theta, and we will now make our parameter theta, or more precisely our parameter vector theta, we will make it latent because it is unknown, so that we can put a distribution over it. And this parameter vector theta is affecting the WI, and this parameter vector theta is taking an hyperparameter, which is an alpha vector. And the most reasonable choice for this parameter vector theta is to use a Dirichlet distribution. So we say the theta vector is distributed according to a Dirichlet distribution over theta given the parameter vector alpha, and our WI is distributed according to a categorical over WI given a theta vector, and here I indicate with the semicolon that the alpha is just a vector of values, and with the vertical line I denote that our parameter vector is also probabilistic, or is like has a probability density function over it in order to make our Bayesian analysis. And let us start with the joint, and the joint is the probability of the theta vector and the w vector. So we associate all the n components in w with a random vector. And this is nothing else than the probability over the theta vector times the probability of the w vector given the theta vector, as it factorizes according to our directed graphical model. And we know that all the w's are independent. This is also the assumption of our sampling. In essence, this is what we mean by IID, independent and identically distributed. And then we can write this as the sum from I0 to capital N-1 over P of WI given the parameter vector theta. Usually, in order to do our estimates, we incorporate the dataset directly into this probability statement, and for this we would say something like the probability over the theta and the w vector being the dataset. And we've seen that the dataset is nothing else as a vector or a set of observations, and it has the same length as we have the plate number n here, so this perfectly works fine. And if we then plug this in, then we get the probability of the theta vector, or in other words the prior, multiplied with the product from I0 to capital N minus 1 over the probability that capital Wi is equal to lowercase wi for the ith Weber observation given the theta vector. And we commonly define this to be the probability of theta and the dataset, which is just a shorthand notation for saying that we observe the dataset in order to make the notation a little less cluttered. And this one over here is the probability of the dataset given the parameter vector theta, or the probabilistic parameter vector theta, and that's of course nothing else than the likelihood. And here we have our prior, which we chosen to be the Dirichlet distribution. But now we are no longer interested in likelihood or maximum likelihood estimate, and instead we want to derive the posterior. So let's look at the posterior, and the posterior is the probability over theta given a dataset. So it's like the inverse of the likelihood, and we can apply Bayes' rule in order to evaluate this. And we will be then getting the fraction, and on top we have p of d given theta with the swapped conditions, then times p of theta divided by p of d. And here we have the marginal. Usually we're not interested in the marginal, so we are working with the proportional. And we see essentially what we have here is some sort of like an inverted arrow, which we'll be doing by the help of Bayes' rule. Okay, so by the proportionality we get p of d given parameter vector theta times p of the parameter vector theta. And if you recall, this is nothing else than what we had up here. So it is nothing else than the joint is a general observation that the conditional is proportional to the joint. And then we can plug this in, just swap the orders. This is p of theta times the product from I0 to capital N minus 1 over p of capital Wi is lowercase wi observation given the parameter vector theta. And usually we can ignore this I here since all of the Webers are distributed identically. So all Wi are distributed identically. And then we can plug in the distributions that we had modeled for both the prior and for this conditional. And then we get first, this is the Dirichlet distribution over the theta vector given an alpha hyperparameter vector multiplied with the product. Again, we keep the product. And then we plug in what we had here. This was nothing else than the categorical over W being Wi, the observation, under the theta latent parameter vector. Well, then let's plug in the distribution set we know. So we know the Dirichlet. The Dirichlet is given as the product, or is proportional to the product from d0 to capital D minus 1 over theta d raised to the alpha d minus 1. And then we have to multiply this with a normalization, or we divide by the normalization, and this will yield the gamma function of the product from d0 to capital D minus 1 over alpha d divided by the product from d0 to capital D minus 1 over the gamma function of alpha d. And then we multiply with the keeping the product here from I0 to capital N minus 1, and the categorical is given as the product from d0 to capital D minus 1 over theta d raised to the indicator function that the ith observation is equal to the dth state. And of course, this naturally encodes, we have the states. And recall, in our case with the weather, we would have 3 states: cloudy, rainy, or sunny. Okay, let's make some simplifications here. And we can ignore the normalization when we work in terms of the proportional. So let's put this down. Let's say it somehow ignore this. And we can here change the order of the product. And also, to be a little more explicit, let's put on brackets, because this product is applying to this term and the double product is applying to this one here. And if we do this, then we get this is proportional to, we are keeping the product from d0 to capital D minus 1 over theta d raised to the alpha d minus 1, and in brackets, times, and then we changed the order of the product here. It's the product from d0 to capital D minus 1 over the product from I0 to capital N minus 1 over theta d raised to the indicator function that our ith river observation is equal to d. Okay, then let's look at what is encoded here. This is nothing else. For instance, let's say we observe a data set with 1, 0, 0, 2, 3, 0, and so on. And then we would, for instance, look at d equals 0. Then we would have something like theta 0 raised to the 0 because 0 is not 1. And we multiply this with theta 0 raised to, well, in this case, 0 and 0 is, 0 equals 0, and then we raise it to the 1. The same is true for the next. Then we would have theta 0 raised to the 0 because 2 is not equal 0, times theta 0 raised to the 0 because 3 is also not 0, and then we have theta 0 to the 1 and so on and so forth. And I think you get where I'm heading. If we then multiply these theta zeros, then essentially we can add up the exponents where we have 1 when our indicator function is hot and we have a 0 if not. So in essence, we can bring the product into the exponent with a summation. So what we have will be the theta d raised to the summation from I0 to capital N minus 1 over the indicator function that wi is d. And then we can simplify further because we have the product here and this product is applying to both components here. We can just put them into one big product over all the states. So we have the big product from d0 to capital D minus 1 over theta d raised to the alpha d minus 1 times, and then this one. And this product then applies to both of these components. And we will call this, which is the summation over the indicator function, we will call this nd. So the nd is then defined as the summation from I0 to capital N minus 1 over the indicator function that wi is equal to d. And essentially what this encodes is the number of times we observe the d state. So let's note this down. This is nothing else than the number of times we observe the d state. And thinking again in terms of our weather, we would then have, for instance, how often we have sunny weather, how often we have cloudy weather, and so on and so forth. Then let's put this together. So we get this is equal to the product from d0 to capital D minus 1 over theta d raised to the alpha d minus 1 times theta d raised to the nd. And then we can use the same idea as before and multiply these two together. The bases are the same, so we can add up the exponents, and we get this is nothing else than the product from d0 to capital D minus 1 over theta d raised to the alpha d plus nd minus 1. Now you might already see where I'm heading towards. Maybe this kind of gives you the hint why we call the Dirichlet a conjugate prior. And so let's put this down. Can you see why the Dirichlet is the conjugate prior? And of course, it is the case because we get a really simple posterior, or we get something that's proportional to the posterior, and we will soon see that it is really simple to posterior, but it is of the same format. And actually, I will already give you the hint, it is another Dirichlet distribution. Okay, but before we get there, let us define this as follows. I will define this with a capital M over the data set given theta. And think of it as something as the posterior likelihood. Well, this is kind of a loose term, but it might still give you some hints on where we will be going soon. But with this M, we can now follow two paths. And the first path will be the full posterior, and the second path will be the map or maximum A posteriori estimate. So let's put this down. This is the maximum A posteriori. And we see that this one, similar to the MLE, will be just a point estimate. So in other words, we are getting out one parameter vector for the thetas, the map estimate. And here we will get a full distribution. And this will be additionally helpful when we, for instance, then want to go further to a predictive posterior and so on. Okay, let us start with the posterior derivation. For this, let us recall the fact that we just derived the posterior over the theta vector, given the dataset D was proportional to the posterior likelihood. And the posterior likelihood was the dataset under the parameter theta. For this, let us define an alpha d prime as an alpha d plus an nd. And if we go back up, then we see this is nothing else than this here. So this will be our alpha d prime. And then we get that our posterior is proportional to the product from d0 to capital D minus 1 over theta d raised to the alpha d prime minus 1. And I hope you can see it now, but you could ask yourself, isn't that just a Dirichlet? So isn't it just a Dirichlet? And that's absolutely correct. It's a Dirichlet, but with a different parameter. So we say that the posterior, given the dataset, is the Dirichlet over the parameter vector theta under a new parameter, the alpha prime vector. And of course, this prime indicates that it is different from the alpha. So let's note this down. It is different from alpha vector. And we then can define the posterior as p of theta, given the dataset D is, well, first we have the normalization, so the gamma function from d0 to capital D minus 1 over alpha d prime divided by the product from d0 to capital D minus 1 over gamma of alpha d prime. Then we multiply with the product, which we had before, which is the product from d0 to capital D minus 1 over theta d raised to the alpha d prime minus 1. And that's the posterior. Nice, isn't it? So we found the posterior to the Dirichlet categorical model is indeed a Dirichlet. And that's why we call it a conjugate prior, because the posterior has the same form as the prior. And I will quickly put some spacers around here in order for us to now continue with the map estimate. But in essence, what we will now be doing is to derive the mode or the maximum of this Dirichlet distribution. And we say theta vector map, and the star indicates that this is the maximum, or in other words, it's the arc maximum over all thetas of our posterior likelihood of the dataset under the parameter vector theta. And we don't just have to take the unconstrained maximum, it is subject to the constraint that the theta values have to sum up to 1. I think this makes sense because otherwise we would have too much or too little probability mass. And in order to find this arc maximum easier, we will now work in the log-posterior likelihood, similar to the maximum likelihood estimate, where we have also preferred the log space. The log space does not change the position of the maximum. Of course, it changes the value of the maximum, but we are only interested in the position, or in other words, the parameters that maximize this posterior likelihood. And of course, I wrote double posterior, so it's log posterior likelihood. And so let us define this with a small m on the dataset D and the parameter vector theta, and it is just the logarithm of the capital M of the given theta. And if we apply the logarithm to this, then first the logarithm turns our product into the sum from d0 to capital D minus 1, and then it brings down the exponent, and the exponent was alpha d plus nd minus 1 times the logarithm of theta d. But now, even with our log posterior likelihood, we still have to incorporate our constraint, so we build Lagrangian to include constraint, and this is similar to what we also did in the maximum likelihood estimate, so that we can then do an unconstrained optimization. And I will call this m hat, and m hat now depends, or is given on a data set, and depends on the theta vector and an Lagrange multiplier lambda, and it is given as the m function of d under the parameter vector theta plus the lambda multiplier of the constraint rearranged to be 0 on one side of the equation, and then we will get 1 minus d is 0 to capital D minus 1 over theta d, and with this we now have an unconstrained optimization that we can easily solve. Bring in together what we have, and then we have m hat to be the summation from d0 to capital D minus 1 over alpha d plus nd minus 1 times the logarithm of theta d, and this is all for the first summation, plus lambda times 1 minus the summation from d0 to capital D minus 1 over theta d. And then, since we have an unconstrained optimization problem, we can use the classical strategy. We take the derivative and set to 0. Surely we have a multivariate minimization, so we do the gradient, but in essence this is the same. And so let us start with the gradient with respect to the theta vector. And I will not do any computation since it is identical for each of the entries of the theta vector. So we will just derive m hat with respect to theta e. And theta e will be the eth component of the theta vector. So let's note this down. This is the eth component of theta vector. And if we do this derivation, then similar to the argument that we also had in a maximum likelihood estimate, we will propagate our derivative over to summation, since these are both linear operators. Then it applies to the product. So the first term is a constant, so a coefficient, we can ignore it. And then we apply to the logarithm of theta d. And if we derive theta d, or logarithm of theta d with respect to theta e, we will first get 1 over theta d, so 1 over theta d, and then we would get the inner derivative, and the inner derivative would be 1 if d is e, or would be 0 if d is non-equal to e, because then we will just do the derivative of a constant. And by this interpretation, we can basically just change the index from d to e and ignore the summation, because all components that are not e, for instance, let's say e is 2, and our summation goes from 0, 1, 2, 3, 4, 5, and so on. If we have, let's say, 6 states, then all the components where d is not 2, so for instance 0, 1, 3, 4, 5, and so on, they will be 0, so we can only account for the eth component. Long story short, we will just ignore the sum and change the indices. So we have alpha e plus ne minus 1 times 1 over theta e plus, and then we have the same game here, only if theta d is e, it will be non-zero, and in this case it will be 1, so we will just get a minus 1, and in this case we have a minus lambda, and this has to hold to 0, so we can rearrange it and get lambda is alpha e plus ne minus 1 over theta e. Okay, then let's continue with the next derivative. Let's derive m hat with respect to lambda. And if we do this, then we will just get back our constraint. This is always in Lagrange multipliers. And we have 1 minus the summation from d0 to capital D minus 1 over theta d, which has to hold to 0. So let's rearrange it, and we get the summation from d0 to capital D minus 1 over theta d is, of course, a 1. But now we have a Lagrange multiplier that we have to eliminate, and we can ask ourselves how to eliminate lambda. And for this we have to apply some tricks, but before we get to these tricks, let us first make some observations. So I will put some space in here, and then we can look at this expression here. So we say lambda is alpha e plus ne minus 1 over theta e, but this lambda is constant independent of what theta e we derive. So if we derive with theta 0, then we will have a lambda. With respect to theta 1, we have a lambda, and so on and so forth. So this lambda, as this fraction here, is identical whether e is e, or so let's say also holds for e minus 1 and e plus 1. So in essence, we can also do like a variable index, which for instance would be d, and define lambda as this. So lambda would be alpha d plus nd minus 1 over theta d. I hope this makes sense. If not, please also take a look at the maximum likelihood estimate derivation, where I discuss this in more detail. And let's argue that lambda is lambda. I think you would agree with me. And this is nothing else than lambda times 1. This also makes sense. Everything multiplied with 1 will be the value itself. And then we know 1 is nothing else than the summation over all the thetas. So we have lambda times the summation from d0 to capital D minus 1 over theta d. And since lambda is nothing else than a constant, we can put it into the summation. And then we get the summation from d0 to capital D minus 1 over lambda times theta d. Then let's plug in the lambda that we just found, and we get the summation from d0 to capital D minus 1, and we get alpha d plus nd minus 1 over theta d multiplied by theta d, and then you see where I was heading. This now cancels, and we are left with the summation over this term. So we have the summation from d0 to capital D minus 1 over alpha d plus nd minus 1. And let's make some further simplifications. Let's split out the sum, which is applying to this entire term, into the sum applying to each of the components individually. And we would be getting the summation from d0 to capital D minus 1 over alpha d plus the summation from d0 to capital D minus 1 over nd minus the summation from d0 to capital D minus 1 over 1. And we can solve two of these sums explicitly. If we have 1 and we add up 1 d times, this is nothing else than d. And if we have our nd, which recall was the number of times we observed the d state, and we add this up, then this is nothing else than n, right? So because in total we have n observations. So we get the following. This is n minus d plus the summation from d0 to capital D minus 1 over alpha d. And this was our lambda, or in other terms, our Lagrange multiplier. And then we can plug this back in. Let me go up here and call the expression that we had here a star, and then plug into star, and then we get n minus d plus the summation from d0 to capital D minus 1 over alpha d is the alpha e plus ne minus 1 over theta e. And recall, we wanted to take the derivative with respect to theta e in order to solve for theta e. So we rearrange for theta e by bringing this expression into the denominator and bringing this expression on the other hand side. And then we get theta e is ne plus alpha e minus 1, I rearrange the order of summation here, divided by n minus d plus the summation from d0 to capital D minus 1 over alpha d. And that is our maximum a posteriori estimate. And also, if you look at it, it's quite similar to what we had for the maximum likelihood estimate, where we just divided ne by n, and now we have some augmentations here. And these augmentations are also sometimes called, or in other words, the hyperparameters are also called pseudo-counts, because in essence we had the ne, which was the number of observations for the e state, and now we add up pseudo-observations, 20 additional observations, and this lets us encode prior knowledge. For instance, if we observed it days before, or if we just know by modeling the Dirichlet distribution that certain alphas or alpha e's are allowed. I mean, surely pseudo-counts, it's a loose term because it can also be a real value, doesn't have to be an integer, but I think you know where we'll be heading. And let's also note down the definition of ne, and ne was nothing else as the summation from I0 to capital N minus 1 over the indicator that wi is equal to e. And also let me note down what this means for the one-hot categorical, which was just a different way of encoding the different states. So for one-hot categorical, and recall in this case we don't have integers 0, 1, 2, 3 and so on, but instead we have one-hot vectors. And with this it would be even simpler. Then ne is nothing else than the summation from I0 to capital N minus 1 over the ith observation index e. Because we know in the ith observation only one of the components is hot, and if the eth component is hot, then this is equal to applying the indicator function. And so this map estimate is valid for both classical categorical and the one-hot categorical. Okay, let's have a look at how the map estimate and the posterior will be modeled in TensorFlow probability. But before we start, if you enjoyed the video so far, then please consider liking and subscribing. I would extremely appreciate this. Okay, for TensorFlow probability, we are now in an interactive Python session, and I already loaded all the packages. Let us first define an array of true theta values. We will be using them in order to create a dataset, and then later on we can compare our map estimate with them. And we will say we have 20% chance of cloudy weather, 30% of rainy, and 50% of sunny weather. Then we can create the weather random variable, and for this we will use a categorical distribution, and we feed in the probabilities according to the thetas array. And if we look at it, then we have the categorical, and we see no bad shape, no event shape, fantastic. We can sample the distribution, and we can, for instance, also sample the distribution 365 times, and then we would get, the weather for every day of the year. For the next stages, it is way easier to work in terms of the one-hot categorical, since we can then easier reduce the values. So let us create another random variable that we call weather one-hot. And for this, we will use the one-hot categorical and feed in the same probabilities array. And if we look at this distribution, then we see, well, it has a higher event shape because we now have a vector encoding for the states, and we can sample the one-hot vector, for instance, once, and then we get, the array 001. And we can also create a dataset, which will just be sampling the one-hot categorical distribution multiple times. And for instance, let us sample it 365 times. Then we have the data set, and we can also note down the number of samples we used, which was 365. Then let's defer the ND, or the number of observations per state, and I will call this N per state, or N per cloudy, N per rainy, and so on and so forth. And for this I will use TF reduce sum over the data set in the 0th axis. Because if you look at the dataset, then it is just a really long matrix, and we reduce along the first axis in order to get the n per state vector, which is just how many times we observe a certain state. So for instance, 68 times cloudy, 106 times rainy. Then we can find an MLE estimate by the formula we derived in an earlier video, which will in our case then just be n per state divided by n samples. And then we have the thetas MLE, and just like this, we inferred 18, 29, 52, so it's around what we would expect. Okay, now we want to define the map estimate, and for this we have to encode the alphas vector. And the alphas vector, they encode either our prior knowledge or our prior observations, however you want to call it. And I will use TF convert to tensor in order to work in a TensorFlow world. And we will have, for instance, 20 for cloudy, we have 30 for rainy, and we have 60 for sunny weather. And we can look at them and see this is the values, and these are our prior knowledge. And now in order to infer the map estimate, we have to convert the dataset into floats, because right now we just worked in integers. And for this I will use n per state is TF cast n per state into a float. Then let's translate our formula for the map estimate, and I will use thetas map. For this I will not only work in theta e, but I will do a calculation for all the thetas at the same time. And for this we will get n per state, so the vector that we just created, plus the alphas, and that's just component-wise addition. And then we subtract 1.0, which will also be a component-wise subtraction. And we divide by the number of samples, which was our n, minus the number of states, which I did not define, but we used 3 states. And then plus TF reduce sum, and then we reduce over the alphas in order to have the summation over all the alphas. And then we can look at the map estimate for the theta, and we see it is different from the MLE estimate, but not too different. You could maybe even argue it's a little bit off in the second component, but anyhow, it is still a valid estimate for our data, and we can probably work with it. But you now might ask yourself, why do you need it then if it's just the same as the MLE? And for this, we will look at some corrupt dataset. And I will create a copy. I will call this dataset corrupt, and I will use dataset.numpy in order to transfer the numpy world, because we want to modify the array. And we will do this as following, in that we set the last element starting at the day 200 all the way to the end to 100. So it was a corrupt observation, and we just observed cloudy weather. And we can look at the corrupt data set and see, well, in the beginning it is still like as we observed it. For instance, here it's rainy, sunny, sunny, and then in the end we only have like 165 cloudy observations. And then we can also infer the n per state corrupt, and n per state corrupt is the same logic as before. We do tf dot reduce sum over the corrupt dataset, but along the 0th axis again, and we have n per state. And this also shows that it is kind of corrupt because we have way more cloudy observations than we would probably expect. And then we can do fetas MLE corrupt, and for this we will again divide n per state, in this case also corrupt, by the number of samples we've drawn. And we do a fetas map. I will just copy this down, and for this we will use also the n per states corrupt, and we call this a theta map for corrupt. And I forgot that the n per state have to be casted into a float, so n per state, and let's cast them into a float, and then it's calculated. And then we can first look at the MLE, and then we look at the corrupt map estimate. And we can see the MLE is more prone to overfitting to the data, because it is really just evaluating the thetas based on the data. But here we have our prior knowledge, which kind of corrected us. It's still off, but it's not as off as the MLE. And if we would have had more or like more precise prior knowledge, then we could have shifted it more towards the correct solution. And that's also the big advantage of the map estimate, to be more robust for those kind of corrupt datasets, noisy datasets, and so on. But so far we only looked at map estimates, and we can also look at posteriors. For this, let us first look at the prior, which would be an Dirichlet distribution with the alphas that we just defined. And then we can do a posterior as the Dirichlet again, but with alpha primes. And recall, alpha primes were nothing else than alphas plus n per states. And then we get the posterior. And we can also do a corrupt posterior, which would be the Dirichlet distribution of the alphas plus the n per state corrupt. And then if we look at the prior, and for instance, if we look at the mode of the prior knowledge that we encoded is that the most likely combination of parameters is this one here, which is kind of close to the true values that we chose. So kind of our prior knowledge that we encoded was in essence correct, or getting close to the true observation. And if we do the same for the posterior, then we are actually getting our map estimate, because the map estimate is nothing else than the posterior of the mode. So if we do the posterior corrupt mode, we are also getting the corrupt estimate. And we can see, of course, the values are off again. But this, of course, was due to the fact that we had the corrupt data. But anyhow, it is coinciding with the map estimate that we calculated earlier. And you can play around with it. You can either sample the posterior, you can sample the prior, look at the mean, and so on and so forth. That's the end of the video. I hope the derivation of the posterior for the Dirichlet categorical model was clear. If you have any questions, then write a comment. I would be happy to answer this. Here you will find similar videos, and then I'm looking forward to see you next time.